I'm going to go over this lysimeter problem in Excel because Excel just makes the calculations so much easier. But I'll also try to show how to do it by hand as well. So first of all, I've opened up Excel and these are the data for the problem. We've got a lysimeter that's quite large. It's 3 meters by, see these cells here, 3 meters by 2.4 meters. That's the area, and it's actually 2.5 meters deep, which I haven't shown here because that's actually not important. And I've already calculated the area of the surface in square meters here. So I just simply wrote equals B1, the content of the cell B1, which is the width in meters, times B2, which is the length in meters. And so the area of the lysimeter, the surface area, is 7.2 square meters. And these are our data. We collect precipitation data in the metric unit of millimeters per day for 5 days, 1, 2, 3, 4, 5. We calculate the drainage at the bottom in cubic meters per day, days 1, 2, 3, 4, 5. And we also calculate we measure the weight of the lysimeter, of the monolith, I should say, the package containing the soil and the grass or whatever the crop is in the water, this giant, huge thing that's 2.5 meters deep by 7 square meters in area, and it's huge, right? And so its mass when we start the experiment is 34,830 kilograms, and at the end of the experiment after 5 days it's gone down to 34,547 kilograms, and we're going to use that to calculate the amount of water that's been lost from the monolith, and we'll use that to calculate ET. So first things I can do, notice precipitations in millimeters per day, and we're going to have to convert that to meters eventually, right? Because we're going to want to do everything. We're going to do everything in the unit of, I'll write it over here, in the unit of cubic meters per 5 days, because it's a 5-day experiment, right? So the first thing I can do is I can just take the total precipitation. I'm going to sum up these cells here. That will give us the total amount of precipitation that fell in the 5 days in millimeters per 5 days. So I just simply use the sum function in Excel. I say the sum of, and I can just highlight these cells, return, and so there were 29 millimeters of precipitation fell over those 5 days. And if I want to convert that to cubic meters that fell over that 5 days, first I need to convert the millimeters to meters, and then I need to multiply by the area. I'll highlight this, the area of the surface area, right? So what I can do here is I can say that is equal to what's in H6, that's my, I'll put in parentheses, that's my total precipitation in millimeters, and I'll divide that by 1,000. So now these are now meters per 5 days, and I'm going to multiply that now times the area, which is found in cell B3. So there you go, that 0.2088, that is the volume of water added to the monolith by precipitation over 5 days. For the amount of water that drained out the bottom, it's even easier. I can just sum these guys up again. Actually, you know what I'm going to do here, just to remind myself maybe. So this is the total over 5 days. And I'm just going to write down the units here so I remember what I'm summing here. So these were actually in millimeters per 5 days, right? But I had to convert them to cubic meters per 5 days. So when I sum up this total of the drainage, now in Excel, this is one of the beauties of Excel. This equation here basically says sum up the values in the previous 5 cells, and that's exactly what I want to do. So I just can copy and paste that equation, and look at that, it does it for me. So this 0.21 is the sum of these 5 values, and that's exactly what I want. And those are actually already, those are in cubic meters per day, so that's the sum of the drainage in cubic meters per 5 days, and that's what I want. So it's the same thing. So I'm just going to write equals H7. Okay, so there is precipitation added water, drainage subtracted water, and we need to now calculate the change in the volume of water lost just due in total measured by the change in weight. So if my initial weight was 34,830 kilograms and our final, I should say mass, was 34,547 kilograms, and the change, I'll just put a change in mass, if that makes sense. I'll just call it, yeah, change in mass in kilograms will be, and that's over 5 days, I can remember that, right, is going to equal B12 minus B11. and it's negative, right? It lost 283 kilograms of water. Now, let me just remind you here how this works here. So the density of something like water is equal to the mass divided by the volume. And in this case, we have the mass. This is a mass here, right? This is the mass in kilograms. And I actually want to convert that to the volume of water that's equal to. So I want to solve this equation for the volume. So just rearranging, I get the volume is equal to the mass divided by the density. And in this case, we know that the density of water is 1,000. I'll just write it down here. The density of water is equal to 1,000 kilograms per meters cubed. That's something you probably should know. So now if I want to make the change in volume of water, right? This is of water in terms of cubic meters, it's going to equal this value negative 283 in B14 divided by the density of water, which was 1,000. So it's negative 0.283. So in other words, during this 5 days, this was over 5 days, right? So maybe I should make that clear. This is millimeters cubed over 5 days. So over the 5-day period that I ran my experiment, there was the total, the monolith lost a water equivalent to 0.283 cubic meters. It received 0.2088 cubic meters of water from precipitation, and it lost 0.21 cubic meters of precipitation from drainage. And the reason I wrote this up here is I could have written that. I'm just going to put that back. Just to remember, this is the change in the water stored in the monolith. It was equal to B15. So I've just kind of put them all in the same column here. So this would be the change in the water stored, volume lost by drainage, volume gained by precipitation. And we're going to write the storage equation here, right? We can do this. Let me do it in red here just to show you how easy this is. We can, for our monolith, we can write that the change in the volume of water stored has to be equal to the water added by precipitation minus the water that was lost by drainage out the bottom, and then minus the water lost by ET. And this is what we want, is ET. That's the thing that's hard to measure. So this is our storage equation for the monolith, for our lysimeter. And so we can just solve this for ET. We can just say, okay, just put ET on one side of the equation. We get ET is going to equal to P minus drainage minus the change in storage. And we have all those things, right? Here's P, there's drainage, and there's the change in storage. You can see my crappy handwriting, okay? And so we just can do this. We can just calculate. Now, just remember our units here. So this is ET, oops, I'm going to calculate it down here. This is ET in cubic meters per 5 days, right? And that's going to equal P, which is in J6, minus D, which is in J7, minus the change in storage, which is in J8. And there it is. So ET is positive. Okay, that's what we want it to be. We've lost water equivalent to, well, we've lost water equivalent to 0.28 cubic meters over the 5 days. So now we just need to convert this. We're asked to give an answer in millimeters per year. So we just have to do some simple little conversions here. So remember though that this is the volume in our monolith and had an area, right? So we're going to have to convert that to a flux by dividing by the area. But first let's go here. Let's just do this ET in meters cubed per day. Okay, just per day. So I'm just going to take the value of meters cubed per 5 days and divide it by 5. So that's meters cubed per day. And then I can do meters cubed per year by saying that value times 365. So that's the cubic meters per year. But now if I want the flux, I have to divide that by the area. The area is the one in the orange cell up here. So remember, so if I want to get ET in meters per year, that's a flux. Now I take the volumetric flow rate, which was 20.574 cubic meters per year, and divide that by the area of 7.2 square meters. So I get B19 divided by B3. Okay, and this is my flux in meters per year, and there you go. It's 2.85. Actually, there's many fewer significant figures there. I shouldn't be showing so many, so oops, wrong way. Let's just go. It's 3. Actually, it's probably about 3. Okay, without going through a detailed analysis. So 2.86 meters per year. That's probably a more useful unit than millimeters per year, but but in the rest of the world, usually precipitation is measured in millimeters. So if I want to go ET in millimeters per year, that's going to be super easy because there are 1,000 millimeters per meter. So I merely need to multiply that value, the one in B20, times 1,000, right? And I get 2,587 millimeters per year. One other way I could have done that, if you wanted to be super lazy, I could have just said ET in millimeters per year was also, I could use my convert function, is convert the value in B20 from meters to millimeters. I would have gotten the same thing, but no reason to go through that when I know that there are 1,000 millimeters in a meter. Sometimes the simplest things are the easiest things. So anyway, there's my answer, 2,857 millimeters per year of evapotranspiration. That's a lot, by the way, so this is probably in a desert climate, determined by using the lysimeter.